Hi, we're Team 42 and our project is SOMAD, Stack Overflow Mining and Analytics of Developer Data. With the advancement in technology, understanding developer compensation has become extremely important and is contingent upon several factors that keep transforming over time. Through this project, we're aiming to provide quantifiable data regarding compensation for software developers. We'll also analyze tech trends over the past few years and the changes in the industry. We'll implement multiple supervised learning approaches based on data modalities and unsupervised learning approaches. We'll perform feature engineering on the data to identify and rank features affecting compensation before model fitting and later analyze their Shapley interactions after model fitting. We'll also intend to use end-to-end GPU acceleration and parallel processing through the data pipeline using the Rapids library and benchmark the performance. Our data set is the Stack Overflow Developer Survey 2022. It has 73,268 rows and 79 columns, of which the target column is the variance salary. Survey questions broadly span over topics like developer profile, educational level, coding technology, salary compensation, etc.
The dataset is heavily categorical, with only work experience being the numeric feature that's all being categorical. On average, about 50% of the data had missing entries. We used multiple strategies to handle missing values based on sparsity of column, data type, and nature. Some strategies used were imputing with median or imputing with none, and also sometimes deleting columns if they were too sparse. Then we normalized the columns, renamed some of them to feed into the tokenizer, and we handled the multi-categorical data by leveraging the count vectorizer to generate 140 encodings. Then for outlier analysis, we remove the 5% of the smallest and the 5% of the largest salaries to avoid data skew. We also filter the columns to so that each class is supported by at least 200 responses. For the feature engineering, we started off with recursive feature elimination with cross-validation. We were able to narrow down the top 10 most influential features this way, and that we later feed into the ML pipeline.
Unsupervised learning uses machine learning algorithms to analyze and learn patterns from unlabeled data. We explore three unsupervised machine learning algorithms: principal component analysis, T-distributed stochastic neighbor embedding, K-means. PCA is a type of dimensionality reduction technique which is used to reduce redundancies or to compress dataset through feature extraction. It projects the data into lower dimensional space while preserving maximum variance. We see that 151 PCA components explain 99% of the variance in our dataset. Unlike PCA, TSNE is a non-linear dimensionality reduction technique. It models each high-dimensional vector in such a way that similar vectors are modeled by neighbor points and dissimilar vectors are modeled by distant points with high probability.
K-means perform the division of objects into clusters that share similarities and are dissimilar to the objects belonging to another cluster. For our data set, the optimal number of clusters for using the elbow method was 3. Also, based on our SHAP analysis and forward selection, we've selected 2 main numerical features with the highest weightage. And we've used K-means plus plus to initialize our centers to speed up convergence. As we can observe, we were able to group our data into 3 clear clusters, and the use of coding is proportional to the work experience. We've used multiple metrics for clustering evaluations and observe that our clustering algorithm performs well.
In order to analyze the impact of work experience and years of coding on compensation, we perform k-means clustering with these features. We use the elbow method in order to find the optimum clusters, which were found to be 3. The counts of these clusters are represented in this bar chart. This is a 3D visualization of the clustering performance. We can see that initially, coding experience does have an effect on compensation. So people with low work experience and low years of coding obviously have a lower compensation. There are also individuals who have high compensation and high work experience, but lower years of coding experience, which probably refers to the managerial section of people. We can see that after a certain increase in the years of coding experience, there is not much of a correlation between salary and coding experience. Thus, coding is helpful mainly in the developer's initial career. We now move on to the main problem at hand: predicting developer compensation using the information in the survey. This was done using supervised learning techniques and 3 variations of our dataset: one that considered all features, one that considered the top 10 features which were selected by the RFE-CV method described previously, and the PCA components which captured 99% of the variance of the dataset. That is, a total of 151 components were used. The different supervised techniques that were implemented include the dummy regressor, which we used as our baseline model, which always predicts a mean value of compensation; decision tree regressor, which builds the regression model in the form of a tree structure based on categorical features; the random forest regressor, which was an ensemble learning method using results of multiple decision trees; the ADA boost regressor, which was an ensemble learning method using a weighted average of decision tree models; and gradient boot and histogram gradient boot regressor, which employed the previous decision tree and the histogram of the data in order to obtain predictions. The cat boost regressor, which is again an ensemble learning method, which derived its results from multiple decision trees but had a robust method of handling categorical features. And XGBoost, which is a parallelized version of gradient boosting.
A multilayer perceptron is a class of feed-forward artificial neural network. It consists of three layers: the input layer, output layer, and hidden layer. An arbitrary number of hidden layers that are placed in between the input and output layer are the computational engine of the MLP. K-nearest neighbor is a non-parametric method that approximates the association between independent variables and the continuous outcome by averaging the observations in the same neighborhood.
Let us now look at some of the results we obtained. We used grid search for tuning hyperparameters. Grid search involves defining a grid of hyperparameter values and then training and evaluating a model for each combination of hyperparameter values in the grid. As we can see here, for adipose regressor with hyperparameter tuning, the R-squared error is much lesser. The first metric we evaluated is the RMSE. This is a measure of the standard deviation of the predicted errors. This plot given here depicts the RMSE score for each model using all features, top 10 features, and using PCA. When we look at the test error while taking all the features, we can see that the cat boost regressor has the least error value. As our data is highly categorical, cat boost regressor works really well. Another insight to be gained here is that the score using top 10 features and all features are close to each other. This implies that top 10 features that were selected from RFE-CV can be used to effectively fit our model. We then use the mean squared error as another metric to measure how close our regression line is to a set of data points. You can see from our plot here that cat boost regressor and MLP regressor performs well with less test error for all features and top 10 features as well. Mean absolute error measures the average of the distances between actual and predicted values. From the plot, we can observe that for all features, the test error is low for cat boost regressor ensemble learning models. The adjusted R-squared error is a modified version of R-squared error. From the plot, we can see that the KNN regressor gave us the least adjusted R-squared value and is performing well with respect to this metric. Mean Poisson deviance score is a special case of the Tweedy deviance with a power of 1. Smaller the Tweedy deviance, the more our predicted value are closer to actual values. As expected, the cat boost regressors and our ensemble models are performing well and have low mean Poisson deviance. We have also derived some insights by analyzing Shapley values. From the first plot, we can see that the greatest positive impact on yearly compensation comes from learning code from colleagues. This is a negative impact on yearly compensation from learning code from online courses, friends, and job training. From the bottom plot, we can see that the languages which are most valuable for positive impact on yearly compensation are OCaml, Scala, and TypeScript.
We used the Rapids library to accelerate selected models on GPUs. We observed huge speedups with TSNE on GPUs about 45 times faster than on CPU. We got a few interesting insights on the models too. PCA and TSNE, although effective in capturing a good amount of variance, were not very helpful. This is because they are inherently designed to minimize variance, and this notion breaks down when most of the features are one-hot encoded. Upon digging, we found that multiple component analysis is a better alternative. Among supervised learning implementations, the tree-based models were the best suited for regression tasks with categorical features, as they inherently modeled the categorical nonlinearity. The boosted family performed the best, closely followed by the random forests. As expected, all of the tree-based models heavily overfitted the dataset without hyperparameter optimization and cross-validation. Through the feature importances and Shapley values, we were able to confirm the obvious important factors like country, coding experience, and work experience on the developer compensation. But we also found that the next best predictor is whether one codes outside of work and whether they learn from their colleagues. Overall, this project gave us a wealth of information on the developer compensation and how to use machine learning techniques to mine and explain heavily categorical datasets. Thank you.